In this video, we're going to be talking about buffers. Now, a buffer is a solution that can resist the change in pH. And it is made of a weak acid, its conjugate base, a weak base, and its conjugate. Now, every buffer is going to have what is called a buffer capacity. This is essentially how well the buffer works. The buffer is going to work the best when the concentration of the acid is equal to the concentration of the conjugate, or when the concentration of your base is equal to the concentration of your depending on if you're using an acidic or a basic. All right. It also works best at air concentrations. Let's look and see how a buffer will work. And we can look at a buffer made of hydrofluoric and its conjugate base. So hydrofluoric acid is our weak acid. Fluoride is the conjugate base. A lot of times when people see a buffer system made of hydrofluoric acid and sodium fluoride, they'll try to make both of those the reactant. But it cannot be the case because that won't make a buffer. If you see hydrofluoric acid and sodium fluoride, that fluoride is the conjugate base. Now, I cannot walk into a stockroom and find an ion. It just doesn't exist. So that's why you will see a counter ion such as sodium or lithium. Remember, if you have sodium fluoride, it is completely soluble in water. So in solution, I only have sodium ion and fluoride. Sodium ion is always soluble, so it's not going to interact with anything else in our buffer system. But this is how we can introduce an initial concentration of both our and the conjugate. Now, the way a buffer works is if I base to my buffer, it is going to react with hydrofluoric acid. We'll have hydrofluoric acid, and it is going to neutralize hydroxide if it is added to make water and fluoride. And in this case, we're introducing more of our conjugate base into our buffer system. So notice, since I neutralize the base when it's added, it's not going to change my pH level. If we add an acid to our buffer system, it is going to react with the conjugate base. And it can make the hydrofluoric acid. So again, we're neutralizing that acid that's added, and we can make more hydrofluoric acid, which is part of our buffer system. All right, let's go and look at an example. We have a buffer is prepared by dissolving 6.3 grams of sodium acetate in 1 liter of 1 molar acetic acid. Calculate the pH of the buffer, and we're given the Ka. Now, keep in mind, the whole purpose of this sodium is to act as a counter ion because acetate does not exist by itself. So this is a counter ion. And the other thing that is important about sodium, is it will always be a spectator ion. And it is not going to participate in the chemistry. So when you're choosing the counter ion, it's very important that it will also always be a spectator ion. So group 1 metals are a great counter cation. So when I write out my buffer system, I need to recognize that my buffer system is going to be acetate and acetic. So acetic acid is going to be my weak acid. And when we look at the reaction of it dissociating in water, it is going to yield hydronium ion, my acid. Remember, I don't care about the sodium because it's not going to participate in the chemistry, so I can just give it like this. Now, the whole purpose of this is to solve for the pH. And I know that the pH is equal to the negative log of the concentration of hydronium ion. When I write out my equilibrium expression for acetic acid, Ka for acetic acid, the concentration of hydronium ion times the concentration of acetate divided by the concentration of my acetic acid. Remember, water is not included because it is a liquid. So I can use all of the information in this problem to solve for the concentration of hydronium ion. I can rearrange my equation to solve for the concentration of hydronium ion, and that is going to be equal to Ka times the concentration of acetic acid divided by the concentration of. Now I have the concentration of my acetic acid. So this is going to be 1.0 times 10 to the negative, no, 1.8 times 10 to the negative 5. We were given that in the problem, the Ka for acetic acid, and we can multiply that with the concentration of acetic acid, and it is a zero point 0.1 molar. And then we're going to divide that by the concentration of our acetate. Now, we need to keep in mind that we're not given the concentration of acetate, we're given the mass of acetate. So I can take the mass of my acetate and I can use it to calculate the moles. The volume of my buffer, as soon as I get the moles, I can divide it by my volume to get the molarity. Now remember, sodium acetate is soluble. It will completely dissociate in water. So in solution, I don't have sodium acetate, I have sodium ions and acetate ions. So I can calculate the number of moles. I have 3 grams of sodium acetate times 1 mole of sodium acetate is going to be equal to, I need to find the molar mass of my sodium acetate. This is very important. I need the molar mass of my sodium acetate. It has the sodium in it. To take that into consideration when I'm looking at the moles I have. The molar mass of sodium acetate is going to be 82.04 grams. Now, if I look at my equation here, of 1 mole of sodium acetate, I'm going to have 1 mole of acetate. It's a 1-to-1 mole ratio. I have 1 mole of acetate over 1 mole of sodium. So when I calculate that out, I see I get 0.077 moles, 0.077 moles. To calculate the molarity, I need to divide it by the volume of the solution. And in this case, it is equal to 1 liter. So my molarity is going to be 0.077 molar. And I can take that number and plug it into my Kw or my Ka to solve for the concentration of hydronium ion. So now that I have my equation and I have values for everything within my equation, I can calculate the concentration of my hydronium ion. I calculate it to be 2.34 times 10 to the negative 5. Now that I have the concentration of my hydronium ion, I can plug that into my pH equation. So the pH is going to be equal to the negative log of my concentration of hydronium ion, which I calculated to be 2.34 times 10 to the negative 5. And that is going to give me a pH 4.63.